How can a point contain the whole if a point has a finite boundary? You know, if the body has a finite boundary, how can it have infinity in it? So I was like, oh, I gotta go back to the drawing board on this one. I was like, that doesn't really work. How do I do this? Well, it turns out that that's gotta be one of the largest errors that is going on in our understanding of physics and our understanding of the way the universe functions and our place in it. That is, that infinity and finite system are opposites instead of complementary. But how can a finite system and an infinite curvature be complementary? How can the two be together? I knew when I was 10 that there was a solution to this, because I knew I was right, because I had seen it in my mind's eye. I instinctively knew it. Actually, most children I talk to, if they haven't gone through that first lesson of geometry, know this. They think of the universe as infinitely big and infinitely small, all embedded into each other to infinity. In general, they think of that as being quite logical. The kids are not the only people that thought of this. Well, that the concept of a universe coming out of a dot is not that outrageous. The current theory of the Big Bang says that we all came out of a dot the size of a Planck's length, 10 to the minus 33 billions of times smaller than an atom, and all of our universe. The only difference here is that this view says, no, it didn't all emerge from one dot that decided to make a universe. All dots contain the possibility of a universe in it. All dots are connected to all other dots. Again, how do you fit infinity in a finite space? And it's crucial that we understand how we did it. Well, when I grew up, eventually I found the solution. I found the answer to this. The solution is what is called a fractal. Now, if I give that equation to my computer and got the computer to just keep making boundaries, keep making smaller and smaller triangles, it would continue to do this to infinity until it heated up, melt down, and I'd have to go and get myself a new computer. But assuming it didn't do that, it would keep making smaller and smaller triangles to infinity. And I could give it a code so that every 5 iteration or 6 iteration, it would zoom in so you could see it again, and then starts making more triangles, and then zoom in, and then so on to infinity. However, although I can place an infinite amount of triangles, I will never exceed the first boundary I made for myself. Never. I just showed you how infinity fits in a finite space, or a so-called finite space. Because you can divide to infinity within the circumference of a circle. What does that mean? Why is that important? We built faster and faster and faster accelerators that cost billions of dollars to build, to get smaller and smaller and smaller and smaller particles. Now we're at like millions of times smaller than an atom particle, actually. And we're building accelerators now in Geneva, in Switzerland, that are costing $300 billion, I believe. 5 countries had to get together to build it, right? To get even smaller particles. Well, if we understand this principle, we would understand very quickly that you can keep building larger accelerators and you can keep getting smaller and smaller particles. You can always keep dividing. So we would give up the search for some fundamental particle and that's going to end the search for particles, and we would start to understand that what we need to discover is the dynamics of the division, not, how far we can go into infinity. Just so that some physicist can put his name on it and get a Nobel Prize for a new particle. Every one of your atoms, every one of your cells has infinite potential in it, has infinite connectivity to everything else. That each one of your atoms is a mini black hole. Because if there's infinite amount of particles in it that can be divided, that means it has infinite mass. It seemed to say as well that the universe would be expanding and contracting. Right? If everything goes towards infinity at the center of all atoms, then the universe is contracting as much as it expands. And I could see how the external part of my existence is the expansive part, and the internal part of my existence is the contractive part. So I started to think in those terms when I was actually 11, and I learned to meditate. A young master of meditation from India taught me to meditate. And I was really excited because I was discovering a whole world within myself that seemed to have infinite potential. So I started to spend more and more time concentrating inward and connecting with that part of my existence. And I started to think that there must be a balance between the expansion of the universe and the contraction of the universe. And the contractive part of that balance equation is the part that generates. And the radiating part is the part that alienates, that destroys. Yet, all of our science, all of our knowledge is based on the radiating part. There's nothing we've really discovered since fire. We explode everything. We put fuel in a rocket, right? Tons and tons of fuel, and we light the bottom, put a few people on top, and pray that they're going to survive the experience. That's our approach. We put fuel in our car, and we explode it in a chamber, and we push a piston up and down. It's all about explosion. And we think the universe is expanding. When much later, I was brought to Georgia Tech to have a conference, kind of a debate with other physicists. These are very well-known physicists, highly regarded, older people that had their students there. And we were talking about things. Some of the students were there. They came in and out. We were, looking at equations. We had all this stuff on the big wall there, on the blackboard. And I showed up with this book. This is the only book I had with me. I had maybe another few. Well, that was my main book. It's called Gravitation. It's a classical book about relativistic equations. It's written by Messner, Thorne, and Wheeler. Those are legends of physics. Wheeler having worked with Einstein and so on. And it's a brick, you can see. And that's why it's called gravitation. When you pick it up, you know everything you need to know about gravity. And I was going through all the equations, and I could see that the physicists were starting to get upset with me. I was, kind of going through, the way they think of the universal dynamics and the universal expansion and all this. And I finally said, okay, if I understand your model right, and I opened Gravitation on page 719, and I said, if this is correct, then the universe is something like this, which they show you after about 1,000 equations. The model for our universe is a balloon with pennies glued to it. So what you do is you take a balloon, you take a bunch of pennies, and a glue gun. And you glue the pennies to the balloon, and the pennies represent galaxies. And then as the balloon inflates, the galaxies move away from each other, generating the universal expansion we observe with the Hubble. It's called the Hubble constant, or the Hubble expansion, and is observed by various modalities, including telescopes. And so I'm going through this with them, and you got to realize these guys are very accomplished physicists, and they're looking at me going, oh my God, this is like kindergarten stuff. If you don't know this stuff, you should go back home and study a little more before you waste our time. And so I was like, well, what I want to know is where is the equation, because I really looked through all your stuff, and where is the equation for this guy? The room became quiet. And I was saying, well, this is definitely a component of the dynamics that are going on, and I said, if you keep drawing, if you don't stop at the face, and you keep drawing the rest of the guy, you'll notice that when the balloon expands, the lungs contract. For every action, there's an equal and opposite reaction. First law of physics. That hurt. Everybody had a blank look on their face, and the room became so quiet you could hear a pin drop. And I could see my dear friend and sponsor across the room going, oh, you're doing damage. Kind of obvious. Completely missed. Obviously, if the universe expands, then something is contracting. And that dynamic of expansion would be a feedback, right? Expand, contract, expand, contract. And it would have a very specific topological structure, meaning it would look in a very specific way. It would have very specific dynamics for things to be able to expand and then contract and so on.